Hello, welcome back to the Cosmic Guide to Sleep. In this quiet moment, let us gaze together at the starry sky. As you lie down to drift into dreams, the stars outside your window may seem like distant points of light, yet behind each of those points lies an astonishing tale of scale and distance. Tonight, let us embark on this journey across time and space in the most relaxed state, to comprehend just how vast the universe we inhabit truly is, and in what minuscule corner our home planet resides. First, let us begin with the most familiar place, our Earth. When standing on vast plains or beaches, the horizon curves in the distance. Earth appears immense, seemingly boundless. We've built sprawling cities and crossed vast continents. All this makes us feel humanity's home is so solid and expansive. Yet this is merely an illusion born of our immersion. A famous photograph known as the pale blue dot completely overturned this perception. On February 14, 1990, as the Voyager 1 probe was about to leave the solar system, at the request of astronomer Carl Sagan, it turned its camera for one last look back at home. From a distance of approximately 6 billion kilometers, it captured a historic photograph. In this image, Earth is merely a tiny speck of light, a pixel almost too insignificant to notice, floating against the vast, dark backdrop of the cosmos. As Sagan described it, every soul we know, every hero and villain in history, every love and hate, every joy and sorrow, has occurred on this speck of dust suspended in sunlight. The scale of this speck is unimaginable against the cosmic backdrop. Let's make some intuitive comparisons. If you could travel at the speed of light circling Earth 7.5 times per second, it would take you only about 1.3 seconds to reach the moon. Reaching the center of our system, the sun, would take a mere 8 minutes. But this is merely our neighborhood. To leave the solar system and reach our nearest stellar neighbor, Proxima Centauri, even at light speed, would take over for years. And the solar system itself is equally insignificant within our home galaxy, the Milky Way. Our galaxy is a vast island of gravity containing at least 100 billion stars. If we were to shrink the solar system to the size of a coin, the diameter of the entire Milky Way would roughly match the width of North America. In this vast ocean of stars, our sun is just one ordinary member among billions. Our entire solar system is but a tiny bubble within this stellar ocean. Yet the Milky Way is not the entirety of the cosmos. With the aid of modern telescopes, we observe that the observable universe contains hundreds of billions of galaxies like our own. They form vast cosmic networks, stretching across the observable cosmos. The observable universe spans approximately 93 billion light-years in diameter. This figure alone exceeds the bounds of human intuitive comprehension. Consider this one light-year is the distance light travels in a single year, roughly 9.46 trillion kilometers. Thus, 93 billion light-years means light would take 93 billion years to traverse from one end of the cosmos to the other. The sheer scale of this space is enough to make any human brain attempting to fully grasp it feel dizzy. Let us now return to the scale of Earth. All the land, all the oceans, all the atmosphere are merely an extremely fragile membrane enveloping the surface of this tiny rocky planet. Earth's diameter is approximately 12,700 kilometers, yet before Jupiter's colossal storm cyclones, Earth appears like a marble, and the Sun could contain 1.3 million Earths. If Earth's history were compressed into 24 hours, all recorded human civilization would appear in the final 1/100th of a second. Recognizing the scale disparity isn't meant to make us feel discouraged or insignificant. Quite the opposite, it reveals the universe's grandeur and wonder. We inhabit such a unique point, small enough to be negligible on an interstellar scale, yet complex and intelligent enough to turn back and begin to comprehend and measure the vast cosmos itself. This seemingly contradictory position is one of astronomy's deepest charms. When we gaze at the night sky, the lights that meet our eyes originate from hundreds, thousands, or even millions of years ago. What we see is the history of the universe, how it appeared when those lights first set forth. When we gaze into the abyss also gazes back at us. Only this gaze spans unimaginable time and space. This realization brings a profound sense of calm. It places our daily troubles in their proper perspective against the cosmic narrative. In the following chapters, we will explore together those interstellar visitors who have entered our field of vision. How did they traverse this immense void to reach the vicinity of our solar system? How do we discover them, study them, and what insights do they offer us? But before that, please first immerse yourself in this sense of vastness. Let your thoughts journey with starlight, traversing the endless void. Recognize that we are both a mere speck of dust in the cosmos, and a means for the universe to understand itself. This dual nature may be humanity's most precious and tranquil experience. You might think astronomy is an esoteric discipline, studying distant galaxies and black holes, utterly disconnected from daily life. Yet in truth, astronomy's pulse is deeply woven into every facet of our existence. As you prepare for peaceful sleep tonight, many seemingly ordinary things around you glow with the light of astronomy. Let's explore these wondrous connections with a relaxed mindset. The most direct example is the time system we use. When you check the time on your phone or schedule your day using a calendar, you are utilizing the earliest fruits of human astronomical observation. A day of 20-4 hours corresponds to Earth's rotation period. A month of approximately 30 days originates from the moon's orbit around Earth, and a year of 360-5 days traces Earth's orbit around the sun. Our ancestors observed the movements of the sun, moon, and stars to create calendars that guided agriculture and established the rhythms of society. To this day, we still live within this web of time woven by celestial movements. Consider also the navigation systems we take for granted. When you use a map app on your phone to find directions, the Global Positioning System GPS is at work. GPS achieves precise location tracking, relies on a network of dozens of satellites orbiting at high speeds. The clocks require corrections based on Einstein's theory of relativity, because Earth's gravity causes time to pass slightly slower. Without these principles of astronomy and relativity, GPS errors would accumulate to several kilometers daily. It is precisely this profound understanding of cosmic laws that makes precise navigation possible. Astronomical research has profoundly influenced our technological advancements. The magnetic resonance imaging MRI technology used in hospitals originated from key algorithms developed by radio astronomers to analyze signals from distant galaxies. The data transmission protocols of the internet we use daily benefit from scientists' needs to manage large scale astronomical observation projects. Even the CMOS image sensor in your phone's camera originated from technologies refined to capture clearer images of the night sky. Beyond these tangible technologies, astronomy offers an intangible worldview. It reveals that all the heavy elements composing our bodies, like calcium in our bones and iron in our blood, originate from the spectacular supernova explosions of distant stars at the end of their lives. We are at our core children of stardust, bound to the cosmos by the deepest kinship. This realization transcends daily trivialities, bringing profound peace. When you lie awake at night, anxious about something, consider this: you and I are both products of billions of years of cosmic evolution. That we can think and feel here now is itself a miracle. Astronomy isn't distant from our lives. It's in our phones, in our sense of time, in how we see the world, even within our bodies. It is a discipline that weaves together the vast and the minute, the distant and the present. The next time you gaze up at the night sky, you will know that those distant points of light are not merely stars, they are fragments of our shared story. They connect past and future, linking the cosmos to the bed where we rest. Having grasped the scale of the cosmos and astronomy's connection to us, let us now focus on a special class of celestial bodies. They are tonight's protagonists: interstellar objects. These mysterious visitors are not native to our solar system. They come from the vast, frigid interstellar space between stars, travelers who journeyed unimaginable distances to reach us. On this tranquil night, let us revisit their story. Literally speaking, interstellar objects are celestial bodies that do not orbit any star, but instead traverse the interstellar void freely. They may be fragments ejected during the formation of other star systems, or debris from colossal astronomical events like galaxy collisions. For a long time, they existed only in astronomers' theoretical predictions, because their relatively small size reflects extremely faint light. Against the vast cosmic backdrop, spotting them was like finding a needle in a haystack. Human imagination about interstellar objects actually dates back a long time. As early as the 1930s, astronomers speculated that such free-roaming celestial bodies, unbound by stars, might exist in the universe, but at that time our observational technology was insufficient to detect their traces. Over the following decades, numerous asteroids and comets within our solar system were discovered. They all obediently orbited the Sun, adhering to Kepler's orbital laws. This kept the notion of extrasolar visitors feeling like a distant dream. Yet scientific progress is always full of surprises. A pivotal moment arrived on October 19, 2017. The Pan-STARS telescope in Hawaii captured an anomalous light point during routine sky surveys. It streaked across the sky at an extraordinary velocity. Initially dismissed as an ordinary comet or asteroid, it stunned the global astronomical community when additional telescopes tracked its path and calculated its trajectory. This celestial body, named the MUA, possessed an extremely high hyperbolic orbital eccentricity. This indicated it did not originate from the solar system. It was an uninvited guest from interstellar space, the first interstellar object ever confirmed by humanity. This discovery instantly ignited scientific fervor and announced to the world that we had finally found the interstellar traveler predicted by theory. MUA's arrival was like a pebble dropped into a tranquil lake. It brought countless questions and speculations. Its shape was highly unusual, resembling an long cigar. Its length was about 10 times its width and extremely rare from among natural celestial bodies. Even stranger, it exhibited non-gravitational acceleration as it flew away from the Sun. This sparked widespread debate about whether it was an alien spacecraft, although the prevailing scientific consensus leans toward a natural origin explanation, such as being composed of solid hydrogen or nitrogen ice. It remains shrouded in many unsolved mysteries. Just 2 years after MUA, a second interstellar visitor arrived. In August 2019, amateur astronomer Gennady Borisov discovered a comet. Follow-up observations confirmed it also originated beyond our solar system. This is Comet 2A Borisov. Unlike MUA, Comet Borisov exhibits distinct comb and tail features. Its behavior and characteristics closely resemble those of comets within our solar system. This suggests interstellar objects may possess diverse forms and compositions. Their arrival is not an isolated event but a cosmic norm. The discovery of these interstellar objects opens a new window for us. By studying them, we gain direct access to material from other star systems. Without launching costly interstellar probes, we can glimpse the mysteries of worlds beyond our own. They are like cosmic messengers, carrying secrets from distant star systems, silently passing through our home. They await our interpretation. With the rapid advancement of observational technology, we anticipate discovering an increasing number of interstellar visitors in the future, each potentially bringing new surprises that challenge our existing understanding. Beyond our slumbering Earth lies a dynamic, interactive universe, and these silently arriving interstellar objects are captivating footnotes in this grand narrative, awaiting our continued storytelling on future nights. Now let us turn back the clock to that autumn of 2017. Upon Haleakala, the dormant volcano in the Hawaiian Islands, the Pan-STARS telescope has always silently scanned the night sky. Its mission was to comb the celestial realm, seeking faint, moving points of light, to ensure no Earth-threatening asteroids slipped through our radar. On an ordinary night, October 19th, it captured a faint speck of light. This speck lay in the direction of Pegasus, with a brightness of just magnitude 20.5. This meant it was millions of times fainter than the dimmest stars visible to the naked eye. Initially designated A2017, U1A indicating its possible asteroid status, no one anticipated this unassuming speck would soon unleash an astronomical storm. Within days of its discovery, a global network of observatories mobilized. Chile's Very Large Telescope, Canada's CFHT, and numerous other instruments swiftly trained their lenses on this uninvited guest, striving to capture its orbital data. When this data was compiled and orbital calculations performed by scientists at the Jet Propulsion Laboratory, a startling result appeared on the screen. This object's orbital eccentricity reached one point to conclusive evidence. In celestial mechanics, an orbital eccentricity of 1 indicates a parabolic orbit. A value greater than 1 signifies a hyperbolic orbit. All planets, asteroids, and comets within our solar system have orbital eccentricities less than 1, meaning they follow elliptical orbits. They are bound by the Sun's gravity, native members of our solar family. Yet a 2017 U1 is traveling along a distinct hyperbolic trajectory. This indicates its velocity exceeds the solar system's escape velocity. It did not originate within our solar system but arrived as an interstellar visitor. After confirming its interstellar origin, it was officially designated 1IU MUA. The prefix 1I signifies the first human minus confirmed interstellar object. The Hawaiian name MUA translates to the first messenger from afar. This name both captures its essence and conveys poetic reverence. As observations continue, more perplexing mysteries emerge. First and most striking was its extreme light variation cycle. By measuring periodic changes in its brightness, astronomers discovered its luminosity fluctuated dramatically by a factor of 10 or more within hours. This phenomenon typically indicates a rapidly rotating object with an extremely irregular shape. Synthesizing all data, scientists inferred MUA might be a slender cigar-shaped, approximately 400 meters long and only about 40 meters wide. Its length minus-to-width ratio reaches a staggering 10:1. This is extremely rare among any asteroids or comets we've observed before. Within the solar system, the closest known objects in shape rarely exceed a 3:1 length minus-to-width ratio. This discovery immediately raises the first question: what natural process could form such a slender, robust object without its own gravity pulling it into a sphere? This was swiftly followed by a second and far greater mystery. As MUA journeyed toward interstellar space after passing the Sun, astronomers predicted its position using precise orbital models. Yet observations by multiple independent teams revealed a discrepancy between its actual location and the predicted position based solely on solar gravitational influence. It was undergoing a subtle acceleration that could not be explained by solar gravity alone. As comets approach the Sun, ice on their surfaces sublimates under heat, expelling gas and dust like rocket engines to generate non-gravitational acceleration. The problem is, in all observations of MUA, whether by the Hubble Space Telescope or Earth's most powerful instruments, no traces of gas or dust were detected around it. No coma, no tail. It appears as a dry, inert rock, an object with no visible propellant, yet exhibiting visible propulsion effects. It's like a ghost ship silently accelerating into the darkness without raising its sails. This puzzle has spawned a variety of hypotheses and explanations. Some scientists propose it might be an object composed of hydrogen ice. Hydrogen ice can exist at extremely low temperatures, but as it approaches the Sun, the hydrogen gas sublimating from its surface is transparent, making it invisible to our telescopes. This hydrogen ice outflow could explain its acceleration without leaving visible traces. However, this theory faces challenges. Traveling through interstellar space, cosmic rays and stellar radiation would easily erode such a fragile hydrogen-ice subject. It would likely fail to complete the lengthy interstellar journey. Another intriguing hypothesis suggests it could be a fragment composed of nitrogen ice, similar to the material found on Pluto's surface. When a nitrogen-rich body is torn apart by its parent star, it could eject such fragments. Nitrogen ice sublimation could also provide sufficient thrust, and its albedo roughly matches the brightness observed in MUA. Of course, its peculiar shape and unexplained acceleration have led some, including Harvard astronomer Professor Avi Loeb, to propose a bolder conjecture. Could it be an artificial object, such as the wreckage of a light sail spacecraft or a defunct space probe? From a distant civilization, whose luminous structure could harness solar pressure for acceleration. While this idea has sparked immense public excitement, the scientific mainstream still favors natural explanations. As Carl Sagan famously stated, extraordinary claims require extraordinary evidence. All current phenomena surrounding UMUA, though challenging existing understanding, remain within the realm of conceivable natural processes, albeit extremely rare ones, regardless of its ultimate nature. UMUA's scientific significance is immense and profound. First, it directly confirms the existence of interstellar objects. Astronomers had long speculated that during the formation of star systems, vast amounts of material are ejected into interstellar space. UMUA's arrival transformed this theory from conjecture into reality. It tells us the cosmos is teeming with such interstellar travelers. They traverse between different star systems, potentially carrying the seeds of life, or at least the complex organic molecules that compose life. Our Milky Way may be far more connected than we imagined. Second, it provides us with an unprecedented research sample, a directly observable celestial body originating from another star system. With our current technology, we cannot launch probes to other star systems to collect rock samples there, yet the universe, in its own way, has delivered samples from other star systems right to our doorstep. Though MUA arrived abruptly and departed hastily, leaving us with limited data, this data is already priceless. It allows us to glimpse how exoplanetary systems form and evolve, and the similarities and differences in their material composition. Finally, and most significantly, UMUA serves as a mirror, reflecting the boundaries and limitations of human understanding. It challenges our established taxonomies, neither a typical asteroid nor a typical comet, forcing astronomers to contemplate that the forms matter can take across cosmic scales may be far more diverse than we imagined. It reminds us that science advances precisely through such anomalies and surprises. When we encounter a phenomenon that existing theories cannot perfectly explain, it is not the end of science, but precisely its most thrilling beginning. Today, UMUA has long since flown beyond the reach of all our telescopes. It is quietly sailing into the depths of Pegasus, carrying its unsolved mysteries. Like a silent messenger passing swiftly through our home, leaving behind a hastily scribbled, barely legible note, we still strive to decipher the message on that note. Its arrival and departure forever altered how we perceive the cosmos. In the boundless void, we are no longer solitary inhabitants. We have become potential members of the cosmic community, awaiting the next messenger. On this tranquil night, as you gaze up at the stars, perhaps you can imagine that within the unseen darkness, countless mochos bearing tales from other worlds are silently gliding by, while the scientific community continues to debate UMUA's many mysteries. Just 2 years later, the cosmos sent a second messenger. This messenger was strikingly different from the enigmatic UMUA. It presented itself as an interstellar visitor in a manner more aligned with our expectations. Its arrival seemed to tell us that the universe holds both exceptions and norms. On August 30, 2019, amateur astronomer Gennady Borisov in Crimea was observing through his homemade 0.65-meter telescope. With extensive comet-minus observing experience, he immediately recognized a new comet-like object while examining captured images. He swiftly reported the discovery. The International Astronomical Union's Minor Planet Center subsequently confirmed and named it to Borisov after its discoverer. The designation to signifies it as the second interstellar object confirmed by humanity. Unlike UMUA, which was identified post-discovery, Borisov was recognized as a comet from the outset, due to its distinct coma and tail hallmark features of comets. The coma is a cloud-like atmosphere surrounding the nucleus, composed of sublimated gas and dust. The tail consists of gas and dust ejected from the nucleus under the influence of solar wind and radiation pressure. These features made Borisov appear as a fuzzy, glowing spot in telescopes. This formed a stark contrast to the pinpoint light of Oumuamua. The global astronomy community mobilized once more. This time, we were better prepared and had more time. Borisov was detected before its entry into the inner solar system, granting us months for detailed observation and study. Top-D instruments like the Very Large Telescope and Hubble Space Telescope tracked its path. Observational data quickly revealed Borisov's fundamental properties. Its nucleus diameter was estimated at approximately 1 kilometer, comparable to many comets in our solar system. Spectral analysis showed its coma contained molecules of cyanide and carbon monoxide, chemicals also common in solar system comets. When it reached its closest approach to the Sun in December 2019, its tail stretched over 160,000 kilometers, equivalent to over 10 times the diameter of Earth, creating a spectacular sight in images. Yet beneath these seemingly ordinary features lie unusual details. Astronomers analyzing dust particles in its coma discovered this dust is exceptionally dry, with water content far lower than typical solar system comets. This suggests Borisov may have formed in an extremely cold region of its parent star system. Alternatively, its surface ice may have been depleted by cosmic radiation during its long journey. Another intriguing discovery is the apparent fragility of its nucleus. After its solar flyby, the Hubble Space Telescope observed possible fragmentation, with at least one fragment separating from the main body. While such breakups are not uncommon among comets, they offer clues to studying their internal structure. Now let us juxtapose these to interstellar visitors for a profound comparative analysis. Oumuamua and Borisov hail from different galaxies, bearing starkly divergent destinies. One resembles a silent, unidentified messenger passing through with haste. The other resembles a diplomat making a grand, proactive declaration of intent. In form and composition, Oumuamua more closely resembles an asteroid, dry and elongated. Borisov, however, is a classic comet, rich in volatiles and possessing a prominent gaseous envelope. This first tells us that celestial bodies ejected into interstellar space are diverse. They may include remnants of planetary formation, members of the cometary reservoir, or even fragments of shattered bodies. Interstellar space is not empty, but filled with various types of interstellar drifters. Orbitali both exhibit hyperbolic trajectories, unequivocally confirming their interstellar origins. Yet Oumuamua's orbit lies nearly perpendicular to the ecliptic plane, as if intruding from above the solar system. Borisov's orbital inclination, however, forms a smaller angle with the ecliptic, suggesting a passage closer to the planetary orbital plane. This suggests interstellar objects enter randomly, without specific preference. Future visitors may arrive from any direction. Most significantly, their successive arrivals have profoundly revised our expectations. Before Oumuamua, we had never detected an interstellar object. After Oumuamua, we assumed all interstellar objects might share its peculiar enigmatic nature. But Borisov's arrival reveals that ordinary interstellar comets may be far more common in the cosmos. Oumuamua might be a rare anomaly, while Borisov represents a more universal pattern. This provides a more reliable estimate of celestial exchange frequency within our galaxy. Some models predict that at any given moment, up to tens of thousands of interstellar visitors may be traversing our solar system's inner regions, though most remain too faint for us to detect. Borisov serves as a standard reference point. Its ordinariness is precisely what makes it extraordinary. It reveals how similar the formation processes of other star systems are to our own. They too eject comets whose chemical composition and behavior mirror our own. This cosmic uniformity offers profound comfort and a sense of connection. We do not inhabit a singular star system. We follow the Milky Way's shared laws of matter and dynamics. This anchors us more firmly within the cosmos. The arrival at Yet They bring not only excitement but profound challenges. Like to rigorous examiners, they subject our astronomical models to comprehensive testing, revealing gaps and limitations in our understanding across several core domains. The first challenge confronts our established models of solar system formation and evolution. Traditional views held our solar system as a relatively isolated entity, where planets, asteroids, and comets formed a stable family. Occasionally, comets from the Oort cloud might be disturbed into the inner solar system, but overall, the system was considered closed, its history self-contained. The arrival of these interstellar visitors shatters this assumption of isolation. They demonstrate that star systems are not isolated entities, but engage in continuous material exchange. This implies that in the early solar system, material from other stellar systems may have incorporated, potentially delivering the water and organic molecules essential for life on Earth. Our origin story may need to be rewritten on a grander, galactic scale. The second challenge concerns astrophysical's understanding of celestial bodies, shapes, and structures. MUA's extreme cigar shape is unprecedented among known solar system objects. Within our solar system, whether asteroids or comet nuclei, most bodies tend towards spherical or slightly ellipsoidal shapes. This is because their own gravity overcomes the material's strength, pulling the object toward hyrostatic equilibrium. Irregular shapes only appear when the object is small enough that its internal strength can resist gravity. Yet at hundreds of meters in size, MUA's gravity should have sufficed to shape it into a more spherical form. Its 10-1 length minus width ratio suggests it may possess exceptionally strong internal structural integrity, or be composed of materials beyond our current understanding. This compels us to consider whether extreme environments in other star systems could forge celestial bodies with unique mechanical properties, types we never imagined. The third and most striking challenge stems from MUA's non-gravitational acceleration. Celestial mechanics is a highly mature field within physics. We can predict celestial orbits under gravitational influence with extreme precision. When we knew non-gravitational forces must be at work. For comets, this is the rocket effect generated by sublimation of the comet nucleus. Yet MUA showed no signs of cometary activity. This leaves an unresolved physics question. What mechanism actually accelerated it? Was it the sublimation of extremely sparse, invisible hydrogen ice, the volatilization of nitrogen ice, or more exotic mechanisms like photo-push? Each explanation currently faces significant difficulties. This unsolved mystery points directly to a blind spot in our existing knowledge. Specifically, what is the complete physical picture of non-gravitational effects for small celestial bodies with unique compositions or structures when approaching stars? The fourth challenge concerns our observational and classification systems. Before MUA, our classification of celestial bodies was clear and binary, either asteroid or comet. But MUA blurs this boundary. It looks like an asteroid yet behaves with cometary characteristics. It cannot be neatly filed into any existing category. This exposes the limitations of our classification system, which is fundamentally built upon observations of a finite sample, the objects within our solar system. When samples from beyond our solar system emerge, potentially representing a broader diversity of celestial bodies, our taxonomy proves inadequate. We require a new classification framework, one more flexible and grounded in physical essence rather than superficial appearance. Finally, these interstellar visitors present both challenges and opportunities for our future exploration programs. They arrive abruptly, depart swiftly, and leave us with an extremely brief observational window. From its discovery to becoming unobservable, MUA was visible for a mere few weeks. This exposes the limitations of our current sky-survey systems in detecting such fast-moving, faint, and dark targets. It is precisely this challenge that has prompted astronomers to begin planning next-generation sky-survey projects. For example, the Space Legacy Observatory at the Vera-C Rubin Observatory, it is expected to detect more such interstellar visitors, potentially even providing advance warning before their arrival. More importantly, they have sparked our contemplation of launching interstellar interception missions. If we could detect the next MUA with sufficient advance notice, would we have the capability to rapidly launch a probe to fly by it, or even land on it, to directly sample and analyze its composition, thereby resolving its mysteries once and for all? The technical and managerial challenges are immense, but the rewards would be revolutionary. It signifies our transition from passively observing the cosmos to actively sampling and analyzing it. In essence, these two messengers, MUA and Borisov, hold value not merely in the information they carry, but in the intellectual impact they deliver. They challenge our assumptions about the solar system's isolation, test our understanding of celestial bodies' shapes and compositions. They challenge our ability to predict orbits with precision, and even the very ways we label phenomena in the cosmos. On the path of science, it is precisely these anomalous phenomena, those that defy easy categorization, and those data points that deviate from model predictions, that propel us forward. They remind us that the imagination of the universe far surpasses that of humanity. Our best response is to remain humble, maintain our curiosity, and keep our telescopes ready to welcome the next distant messenger. Upon it, we may find keys to unlocking old questions and inevitably discover gateways to new ones. When a visitor from deep interstellar space quietly enters our solar system, how can we detect it? And how can we decipher the information it brings? All depends on humanity's extended senses, our scientific observation tools. Like cosmic interpreters, they transform faint signals from afar into scientific data we can comprehend and analyze. On this tranquil night, let us step into the world of astronomical observation and understand how those massive lenses and precision radars reveal the universe's secrets to us. The first step in discovering interstellar visitors is often accomplished by wide-field survey telescopes. These telescopes function like security cameras for the cosmos, continuously monitoring vast swaths of sky. Their work may seem monotonous, yet it is absolutely vital. The Pan-STA, our telescope in Hawaii, stands out among them. Equipped with a massive 1.4 billion pixel camera, each exposure captures a sky area equivalent to the full moon. Every few nights, it scans the entire visible sky. By comparing images of the same sky region taken on different nights, computer programs can automatically identify faint, moving points of light. This is how MUA was discovered, a bright spot that shifted a few pixels against the stellar background. And so the story began. But merely spotting a moving light point is far from sufficient. We also need to know what it is, where it came from, and where it's headed. This is where larger telescopes around the world take over for follow-up observations. Take the very large telescope at Perón Observatory in Chile, for example, comprising for 8.2 meter diameter telescope units. It gathers enough light to perform detailed spectral analysis of faint celestial objects. Spectra act like fingerprints for celestial bodies. When light passes through a star's gaseous envelope or reflects off its surface, it leaves specific absorption or emission lines. By analyzing these signatures, we can determine which chemical elements the object contains, and even infer its physical conditions, such as temperature, density, and pressure. For fainter, more distant targets, we must call upon the eyes in space. The Hubble Space Telescope, operating above Earth's atmosphere, unhindered by atmospheric turbulence and scattered light, captures exceptionally clear images. It was the Hubble telescope that continued tracking MUA after it faded into the distance and confirmed its non-gravitational acceleration behavior. It was also the Hubble telescope that detailed the structure of comet Borisov and even captured signs of its potential fragmentation. These space observatories provide observational quality unattainable from the ground. Yet all these optical telescopes share a common limitation. They can only passively receive light reflected or emitted by celestial bodies. We are like observers standing on the shore, watching ships drift by in the distance. We can only guess at their nature through their appearance and lights. But what if we could actively send a signal to them and receive an echo? This is the power of radar astronomy. It transforms us from passive observers into active detectors. The principle behind radar observation is actually quite simple. It involves transmitting a powerful beam of radio waves toward a target celestial object, then receiving the faint signals reflected back after these waves encounter the object. By analyzing the echo's intensity, time delay, and Doppler shift, we can obtain critical information unavailable through optical observation. First, radar can determine the distance of celestial bodies with extreme precision, with accuracy reaching tens of meters or even meters. This far surpasses optical precision and is crucial for determining precise orbital paths. More importantly, radar can penetrate dust and gas envelopes surrounding celestial bodies, directly revealing their surface physical properties. By analyzing the intensity distribution of echoes, we can construct shape models of celestial bodies and even map their rough surface topography. Within our solar system, radar observations have revealed the peculiar shapes of numerous asteroids. Some resemble dumbbells, others peanut shapes, and some even possess their own satellites. Had we had the opportunity to conduct radar observations of Oumuamua at the time, we might have directly unraveled the mystery of its unusual shape, determining whether it was a slender cigar or a flat pancake. Radar observations also reveal a celestial body's surface roughness and composition. A smooth surface reflects radio waves directionally like a mirror, while a rough surface scatters echoes in all directions. By analyzing echocharacteristics, we can infer whether the surface is covered in fine sand, strewn with boulders, or composed of hard metallic material. This information is crucial for understanding a celestial body's formation and evolutionary history. Currently, the world's most powerful planetary radar systems are the Arispo Observatory in Puerto Rico and the Goldstone Observatory in the United States. They have performed detailed radar imaging of numerous near-Earth asteroids, revealing their diverse morphological features. However, radar observations have limitations, including a relatively short effective range. For rapidly departing interstellar visitors, we often lack sufficient time to organize successful radar observations before they enter the effective detection range. This is precisely the regret we face in the case of Oumuamua. In the future, to better study interstellar visitors, we need a more sensitive and faster global observation network. When ground-based telescopes detect a suspicious target, this network can respond swiftly, mobilizing global telescope resources for tracking observations. Multi-wavelength combined observations from optical to infrared, from spectroscopy to polarization measurements, can provide comprehensive information about celestial bodies, and if the timing is right, radar observations should become standard practice because they can provide decisive data on shape and surface characteristics. Additionally, we must develop more powerful data processing capabilities. Modern sky-survey telescopes generate tens of terabytes of data each night, rapidly and accurately sifting through this data to identify unusual moving objects requires increasingly intelligent algorithms and artificial intelligence. These systems learn the normal behavior of celestial bodies and keenly detect any anomalies. The next interstellar visitor may be hidden within tonight's date, awaiting recognition by these intelligent algorithms. As we lie in bed imagining those massive telescopes strained upon the night sky, we can feel a wondrous connection. These precision instruments of humanity stand silent sentinels atop mountains, in deserts, and even in Earth's orbit. They are extensions of our perception, our gaze cast into the depths of the cosmos. With every blink, they may capture a distant messenger. They never sleep, watching the endless darkness for us, listening for the universe's faintest whispers. While we sleep, these sentinels of science remain awake, guarding humanity's window to the cosmos, awaiting the next distant visitor's knock. When we catch a moving speck of light in the night sky, the first question that often springs to mind is, where did it come from? And where is it going? Answering this seemingly simple question requires the aid of an ancient and precise science, orbital mechanics. The principles of this science determine how we understand the dance of celestial bodies in the cosmos. Tonight, let us relax and explore the mysteries behind it together. The first step to understanding orbital calculations is to journey back for centuries to the era of Kepler and Newton. By analyzing the meticulous observational data left by Tycho Brahe, Johannes Kepler discovered the three laws of planetary motion. He realized that planetary orbits are not perfect circles but ellipses. The sun lies at one focus of this ellipse. This is the famous first law of Kepler. His second law describes the changing speed of a planet as it moves along its orbit. As a planet approaches the sun, its speed increases. As it moves away, its speed decreases. Like a dance spinning through the cosmos, the rhythm shifts with distance. Yet Kepler described the phenomena without explaining the cause. This task fell to Isaac Newton. In his 1687 publication, Mathematical Principles of Natural Philosophy, he proposed the law of universal gravitation and the three laws of motion, laying a solid mathematical foundation for orbital mechanics. The law of universal gravitation tells us that any two objects in the universe exert an attractive force upon each other. The magnitude of this force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. This simple formula possesses the power to explain everything from falling apples to planetary orbits. Applying Newton's laws to celestial motion, we can derive Kepler's empirical laws and further reveal that celestial orbits can be not only elliptical, but also parabolic or hyperbolic, depending on the body's total energy. When total energy is negative, the body remains gravitationally bound in an elliptical orbit. When total energy is positive, the body can escape gravitational confinement in a hyperbolic orbit. This crucial distinction is precisely how we determine whether a celestial body originates from interstellar space. In practical calculations, astronomers require observational data from at least 3 different time points. Each observation records the celestial body's position in the sky, specifically its right ascension and declination. Using these 3 positional points, we can preliminarily calculate its orbital elements. These elements include 6 parameters: semi-major axis, eccentricity, inclination, ascending node longitude, etc. Together they fully describe a celestial body's motion in space. However, initial calculations are often quite rough. As observational data accumulates, we can refine the orbit using mathematical tools like the least squares method. This process is akin to gradually discerning a path through the fog. Each additional observation point increases the certainty of the orbit. When sufficient data is available, we can even detect minute orbital perturbations, such as the non-gravitational acceleration exhibited by UMUA. Velocity analysis represents another crucial aspect of orbital computation. By examining the Doppler shift in an object's spectral lines, we can precisely measure its radial velocity, the component of its motion toward or away from us. When an object recedes, its spectral lines shift toward the red end of the spectrum. As it approaches, the lines shift toward the blue end. This displacement is directly proportional to its velocity. Combined with its proper motion across the sky, we can derive a complete 3-dimensional velocity vector. For interstellar visitors, velocity analysis is particularly crucial. Objects within the solar system constrained by the sun's gravitational pull typically do not exceed the solar system's escape velocity. At a distance of 1 astronomical unit from the sun, this velocity is approximately 42 kilometers per second. Interstellar visitors, however, often possess velocities significantly higher than this value. MUA's perennial velocity reached 87 kilometers per second. Comet bursts have also exceeded 50 kilometers per second. Such high velocities themselves provide compelling evidence of their interstellar origin. The precision of orbital calculations depends not only on the quality of observational data, but also on our understanding of the solar system's gravitational field. In computations, we must account not only for the sun's gravitational pull, but also for the gravitational influences of the major planets and even some smaller asteroids. For objects making close planetary flybys, these perturbations can be quite significant. Modern orbital calculations have achieved astonishing precision. For instance, we can predict solar and lunar eclipses centuries in advance, or guide probes to land precisely on targets hundreds of millions of kilometers away. When Oumuamua was discovered, observatories worldwide shared observational data within hours. Orbital specialists worked through the night and soon reached a startling conclusion. This object's orbital eccentricity reached 1.2. This indicated its origin from interstellar space and its eventual return there. This conclusion wasn't mere conjecture but stemmed from rigorous mathematical calculations, a perfect application of Newton's laws in the modern era. Yet orbital mechanics isn't infallible. When Oumuamua exhibited acceleration unexplained by gravity, scientists recognized the need for non-gravitational explanations. This process itself exemplifies science's self-correcting nature. When observations contradict theoretical predictions, we do not dismiss the observational data, but instead consider under what conditions the theory requires extension or revision. Understanding the principles of orbital calculation not only allows us to appreciate the beauty of science, but also helps us identify truly extraordinary celestial bodies. The next time you hear about the discovery of a peculiar celestial object, pay attention to its orbital parameters, particularly its eccentricity. If this value is significantly greater than 1, you may be witnessing the arrival of yet another interstellar visitor. Orbital mechanics is like the grammar of the cosmos. It dictates how celestial bodies should move and interact with one another. Each interstellar visitor's arrival is another validation of this grammar and an opportunity to discover new rules. On this tranquil night, countless celestial bodies follow the laws of orbital mechanics, performing an eternal dance upon the cosmic stage, and we, by understanding these rules, we catch a glimpse of this magnificent dance. In this moment before sleep, perhaps you can imagine yourself floating through the cosmos, feeling those invisible lines of gravity, gently yet firmly guiding the journey of every celestial body. Orbital calculations are not merely cold mathematics. They are a way to understand the universe. When we compute the orbit of a celestial body, we are actually conversing with the cosmos, deciphering the traces it leaves behind, and unravel the story behind it. This pursuit from ancient times to the present has been the inexhaustible driving force behind humanity's exploration of the stars. Tonight, let this curiosity about the cosmos accompany you into your dreams. In your dreams, perhaps you too can become like those interstellar visitors, freely traversing among the stars, dancing along elegant orbits to a cosmic melody. When a faint glimmer from a distant interstellar visitor reaches our telescopes, the information it carries is far richer than we imagine. This sliver of light is like a miniature encyclopedia, recording the celestial body's temperature, composition, and physical state. And the key to deciphering this celestial text is spectral analysis. Tonight, let's approach this wondrous science with the most relaxed mindset. Understanding spectral analysis begins with a simple experiment. When white light passes through a prism, it unfolds into a beautiful rainbow. This rainbow is the continuous spectrum of the sun. Yet, upon closer inspection of the solar spectrum, countless faint arc lines appear against the rainbow background. These lines resemble special codes left by the cosmos, awaiting scientists to decipher them. The secrets of these spectral lines were unveiled in the 19th century by Kirchhoff and Bunsen. They discovered that each chemical element possesses unique spectral characteristics, just as every person has unique fingerprints. When elements are heated to a gaseous state, they produce bright emission lines. Conversely, when continuous spectra pass through cooler gases, absorption lines are formed. By analyzing the positions and intensities of these spectral lines, we can determine the chemical composition of celestial bodies, and even calculate elemental abundances along with physical conditions like temperature and pressure. Spectral analysis of interstellar visitors primarily falls into several categories. Reflected spectra help us understand the material composition of a celestial body's surface, much like how we learn about lunar soil through the moon's reflected light. When we obtained MUA's reflected spectrum, we discovered it exhibited a faint reddish tint. This suggests its surface may contain abundant organic material or have undergone prolonged exposure to cosmic rays. This color resembles certain objects in the outer solar system, providing clues to its possible origin. Emission spectra reveal information about gases surrounding celestial bodies. When comet Borisov approached the Sun, emission lines of cyanide and carbon monoxide were detected in its coma. These spectral lines act like chemical element ID cards, clearly indicating the presence of these molecules. By measuring the intensity of spectral lines, we can estimate the production rates of these gases, and thereby infer the activity level of the comet's nucleus. Absorption spectra function like cosmic filters. When light emitted by a celestial body passes through its own atmosphere, or the interstellar medium, light at specific wavelengths is absorbed, forming absorption lines. By analyzing these absorption lines, we can determine which substances the light encountered along its path. This is akin to assessing the material of a curtain. To determine the curtain's material, modern astronomical spectrometers have become extremely precise. They can split faint starlight into thousands of channels, each corresponding to a specific wavelength. It's like observing a celestial object through thousands of colored filters simultaneously. Such high-resolution spectra reveal greater detail, such as the object's rotation speed, magnetic field strength, and even isotope ratios within its atmosphere. For the spectral observation of Comet Borisov, scientists utilized multiple large telescopes worldwide. By comparing its spectrum with laboratory data, they discovered the comet contains a significant amount of dust. The particle size distribution of this dust differs from that of comets in our solar system. This finding suggests that the planet formation processes in other stellar systems may exhibit subtle differences compared to our own solar system. Spectral analysis also reveals a celestial body's temperature information. According to Wien's displacement law, the peak wavelength of an object's thermal radiation is inversely proportional to its temperature. By measuring an object's brightness across different wavelengths, we can calculate its surface temperature. Spectral observations of MUA indicate its temperature variation aligns with expectations for an inactive surface, consistent with its lack of significant cometary activity. When we combine spectral analysis with orbital data, we can construct a more complete portrait of celestial bodies. For instance, chemical compositions measured through spectroscopy can help us understand observed non-gravitational effects. If spectral signatures of abundant volatile substances are detected, it may explain why certain celestial bodies exhibit unexpected acceleration. The power of spectroscopy extends beyond this. By analyzing the Doppler shift of spectral lines, we can also measure an object's radial velocity. A shift toward the red end indicates the object is moving away from us, while a shift toward the blue end indicates it is approaching. This principle is not only used to measure the velocity of interstellar visitors, but is also widely applied in the detection of exoplanets. It is worth noting that spectral observations require sufficient photons for rapidly fading interstellar visitors. The observation window is extremely precious. This necessitates coordinated efforts from a global network of telescopes. When observatories on one side of Earth enter daylight, telescopes on the opposite side can continue observations, ensuring no opportunity to capture spectra is missed. With technological advancements, we can now conduct spectroscopy observations in the near-, infrared and mid-infrared bands. These bands are particularly sensitive for detecting water ice, organic compounds, and other molecules. The James Webb Space Telescope's infrared spectroscopy capabilities will provide unprecedented tools for studying future interstellar visitors. Spectral analysis is like unlocking the universe's chemical laboratory, allowing us to remotely analyze the composition of celestial bodies billions of kilometers away. This capability is revolutionary in human history, marking a shift from merely observing the positions and motions of celestial objects to entering a new era where we can analyze their material composition, Each time we obtain the spectrum of an interstellar object, it is like reading a letter from afar, written in the universal chemical language of the cosmos. By deciphering this language, we not only understand the object itself, but also glimpse the characteristics of its home star system. This dialogue across time and space is one of the most captivating charms of modern astronomy. On this tranquil night, as you gaze upon the starry sky, perhaps you can imagine that those seemingly tranquil starlights are each narrating their own stories. The spectra encode information about temperature, composition, and motion, like countless cosmic codes, awaiting those with the will to decipher them. And it is precisely through deciphering these codes that humanity gradually expands our understanding of the universe. Spectroscopy reveals to us that the cosmos communicates with us not only through gravity, but also transmits information via light. The next time you see a rainbow, take a moment to consider, behind this simple phenomenon of color dispersion lies a wondrous key to deciphering the universe's composition. Let this curiosity about the cosmos, accompanied by the rich information held within the spectrum, gently guide you into your dreams. In your dreams, perhaps you too can become a beam of light, traversing interstellar space, leaving your own spectral imprint across the vast universe. When night falls and all is silent, as you gaze alone at the starry sky, have you ever pondered this question? In this boundless universe, are we truly alone? Humankind has sought the answer to this question for millennia. Only in the past half-century have we begun to systematically search for it through scientific methods. The birth of the SETI Search for Extraterrestrial Intelligence program stemmed from a simple yet profound realization. If other intelligent civilizations exist in the cosmos, they likely use radio waves much like we do. In 1960, astronomer Frank Drake conducted the first modern SETI experiment. He aimed a 26-meter radio telescope to nearby stars in our solar system. Though the project, known as Project OSMA, failed to detect any signals, it pioneered the scientific search for extraterrestrial life. The following year, Drake proposed the famous Drake equation, which attempts to estimate the number of intelligent civilizations that could exist in the Milky Way. It considers multiple factors including star formation rates, the proportion of stars with planet, and the number of planets suitable for life. Although the values for each factor are highly uncertain, this equation provides a systematic framework for approaching the question, transforming philosophical speculation into a path for scientific exploration. SETI research primarily unfolds along two directions. First, listening for natural signals from the cosmos, hoping to capture intentional or accidental radio transmissions from extraterrestrial civilizations. Second, actively sending messages outward, like casting letters into the cosmic ocean, in the hope of receiving an echo someday. In the listening phase, scientists primarily seek two types of signals. First, narrowband radio signals. These act like cosmic beacons, as nature rarely produces signals with such pure frequencies. If we detect a strong narrowband signal at a specific frequency, it could very well be the work of intelligent life. Second, broadband pulse signals. These may correspond to the communication methods of more advanced civilizations. One of the world's largest SETI projects is led by the SETI Institute. They utilize the Allen Telescope Array in California. This array, composed of 42 small radio telescopes, can simultaneously monitor multiple star systems. Its unique advantage lies in its ability to continuously observe the same region of the sky for months at a time, greatly increasing the likelihood of detecting faint signals. Another crucial observatory is the Arispe Observatory in Puerto Rico. Before its collapse, it was the world's most powerful radio telescope. It participated in multiple SETI projects, including the famous Arispe message transmitted to the globular cluster M13 in 1974. This 3-minute message encoded fundamental human knowledge from DNA structure to the composition of our solar system, though it may take 25,000 years to receive a possible response. This act itself symbolizes humanity's determination to extend a hand of friendship to the cosmos. Beyond radio waves, scientists are also exploring other potential communication methods. Optical SETI searches for possible extraterrestrial laser signals, while neutrino communication probes gravitational wave signals. All are under investigation. After all, a civilization millions of years more advanced than ours might be utilizing communication technologies we cannot even imagine. The debate surrounding active transmission of information is far more contentious. Many scientists, including Hawking, have warned of the risks associated with actively contacting extraterrestrial civilizations. This is the famous Great Filter theory. It posits that some mechanism may exist in the universe that prevents intelligent civilizations from advancing to the stage of interstellar travel. By actively revealing our location, we may invite unforeseeable dangers. SETI research faces numerous technical challenges. First is the task of searching for signals within the vast parameter space. We have no idea from which direction the signal might come, what frequency it might use, or how it might be modulated. It's like searching for a specific needle in a haystack the size of the universe. Second is distinguishing natural signals from artificial ones. The cosmos is filled with various natural radio sources, such as pulsars, quasars, and cosmic microwave background radiation. Scientists must develop complex algorithms to identify potentially intelligent signals. In recent years, artificial intelligence technology has played a crucial role in this endeavor. The 1997 film Contact vividly portrays the work of SETI scientists. Jodie Foster's character spends countless nights wearing headphones, intently listening to sounds from the cosmos. Adapted from Carl Sagan's novel, the film authentically captures the dedication and passion of SETI researchers. The closest historical encounter with a potential extraterrestrial signal was the 1977 WOW signal. A radio telescope at Ohio State University detected an intense signal lasting 72 seconds. When astronomers circled this signal on the data printout, they wrote the word WOW in large letters. This signal matched many expectations for an interstellar transmission. Regrettably, it never repeated. It remains an unsolved mystery to this day. With technological advancements, SETI research is entering a new phase. The Breakthrough Listen project, funded by Russian entrepreneur Yuri Milner, is currently the largest SETI initiative. It employs several of the world's largest radio telescopes, including the Green Bank Telescope in the United States and the Parkes Telescope in Australia, to conduct systematic searches of millions of stars. In recent years, a new research direction has emerged seeking signs of extraterrestrial technological features. This includes detecting massive structures potentially built by extraterrestrial civilizations, such as Dyson spheres, giant structures that could envelop stars to harvest energy, or searching for alien probes that might already be within our solar system. This creates an intriguing intersection with the interstellar visitor studies we discussed earlier. China is also playing an increasingly significant role in SETI. The 500-meter aperture spherical radio telescope (FAST), with its unparalleled sensitivity, is currently conducting multiple SETI research projects. It can detect fainter and more distant potential signals. The significance of SETI research extends far beyond the search for extraterrestrial life. It drives the advancement of radio astronomy technology, promotes innovation in signal processing algorithms, and, more importantly, compels us to contemplate humanity's place in the cosmos and examine our own civilization. Even if we never find extraterrestrial signals, the search itself holds immense value. It embodies humanity's curiosity about the unknown, our yearning for connection, and our quest to understand our place in the cosmos. On this quiet night, knowing so many telescopes are pointed at the stars, listening for the universe's faintest whispers, do you feel a special connection? We may be but a fleeting moment in the cosmos, yet our curiosity transcends time and space. SETI research teaches us science requires patience. It may take generations to find answers, or perhaps we'll never find them, but this persistence itself is worthy of respect. Now, as you prepare to sleep, perhaps imagine On some distant planet, another intelligent life might also be gazing at the stars, contemplating the same questions. This resonance across space and time may be the most precious gift SETI research offers us. In this universe full of uncertainties, we can be certain of at least one thing: humanity will never cease to yearn for the stars, nor stop seeking answers to our loneliness. Let this curiosity accompany you into peaceful dreams. In your dreams, perhaps you may hear greetings from distant galaxies. In our quest to discover whether other intelligent life exists in the cosmos, we encounter a perplexing contradiction, named after physicist Enrico Fermi, known as the Fermi paradox. Its core question is simple: if the universe is so ancient and vast, it should teem with life and civilizations. So where are they? Fermi posed this famous question during a 1950 lunch conversation. Based on the understanding of the cosmos at that time, the Milky Way alone contains hundreds of billions of stars, many billions of years older than our Sun. If a civilization had developed just 1 million years before us, they should have had ample time to colonize the entire galaxy. Yet we see no signs, hear no signals. This seemingly simple question harbors profound doubts about our place in the universe. For decades, scientists have proposed various hypotheses to explain this paradox. One of the most thought-provoking is the dark forest hypothesis. The dark forest hypothesis was systematically elaborated by Chinese science fiction writer Liu Cixin in his The Three-Body Problem series. However, this concept had long existed within the scientific community. It envisions the universe as a dark forest. Each civilization is a hunter armed with a rifle. They stalk through the woods like ghosts, gently parting obstructing branches, striving to make not a single sound with their footsteps. Even breathing must be done with utmost caution. In this metaphor, the hunter must be vigilant, because the forest is filled with other stealthy hunters like himself. If he discovers another life form, there is only one course of action: to fire and eliminate it. In this forest, others are hell itself, an eternal threat. Any life that reveals its existence will be swiftly annihilated. The dark forest hypothesis rests on two fundamental axioms. First, survival is civilization's primary imperative. Second, civilizations grow and expand, yet the total mass of matter in the universe remains largely constant. From these two axioms, an unsettling conclusion emerges. One civilization cannot determine another's benevolence, nor can it discern another's judgment of its own benevolence. Once formed, this chain of suspicion is difficult to break. Ultimately, the safest choice is preemptive action before revealing one's position. This hypothesis offers a possible explanation for the Fermi paradox. The universe is so quiet, not because life is absent, but because all intelligent civilizations have chosen silence. Like creatures in a dark forest, they hide cautiously, avoiding becoming targets to others. However, the dark forest hypothesis is not the only explanation. Numerous other theories attempt to resolve the Fermi paradox, some more optimistic than the dark forest. The Great Filter hypothesis posits that one or more nearly insurmountable barriers exist in the progression from simple life forms to interstellar civilizations. This filter may have been present in our past, or may lie ahead in our own future. If the filter lies behind us, it means our ability to reach our current stage is exceptionally fortunate. This could explain why we see no other civilizations, as the vast majority of life perishes at some early stage. Potential filters include the origin of life itself, the formation of complex eukaryotic cells, or the emergence of intelligence. If the filter lies ahead of us, it implies nearly all civilizations perish upon reaching a certain stage. This could stem from self-destructive tendencies in technological advancement, such as nuclear war, bioengineering accidents, or runaway artificial intelligence, or encountering some inevitable cosmic catastrophe. Another possibility is that we are searching in the wrong way. It's like someone searching for fireflies in a dark forest, using only hearing instead of sight. Perhaps extraterrestrial civilizations communicate in ways we cannot comprehend at all, or they exist in higher dimensions, parallel to us, never intersecting. The zoo hypothesis offers a more benign explanation. It suggests that extraterrestrial civilizations have discovered us, but choose not to make contact. preserving Earth as a cosmic zoo or nature reserve, to observe our natural evolution, just as we observe animals in nature reserves. Another possibility is that we arrive too early or too late. Cosmic civilizations may exhibit explosive growth patterns, and we happen to be in the quiet interlude between two such civilization booms. Or perhaps the early cosmic environment was unsuitable for complex life, and we are actually the first species to achieve intelligence. The laboratory hypothesis posits our universe might be a simulated environment created by a more advanced civilization, much like we create computer simulations. In this scenario, other civilizations may not exist at all, or exist only outside the parameters of the simulation program. Faced with so many competing explanations, how should we approach this? The scientific attitude is to remain open-minded while prioritizing evidence. Though logically consistent, the dark forest hypothesis remains ultimately a reasoning model based on limited information. When observing interstellar visitors like Oumuamua, the dark forest hypothesis naturally springs to mind. Could this enigmatic object be a probe from another civilization? Its cautious trajectory, its precise observation of our solar system, do these suggest some surveillance mission? Yet we also witness celestial bodies like Comet Borisov, which behaves entirely naturally, reminding us that most anomalies in the cosmos may ultimately find natural explanations. When evaluating these hypotheses, we must consider humanity's own developmental experience. Throughout history, encounters between civilizations have not invariably ended in conflict. Examples of exchange, cooperation, and mutual prosperity also exist. Though the logic of the dark forest is unsettling, perhaps the laws of survival in the cosmos are far more diverse than we imagine. It is worth noting that, even if the dark forest hypothesis holds true, that does not mean we should cease exploration. On the contrary, understanding potential risks can guide us toward more cautious space exploration and SETI research, such as exercising greater prudence when actively transmitting messages, and adopting more comprehensive approaches when interpreting anomalous signals. The scientific community indeed holds divergent views on active message transmission. Some scientists advocate maintaining silence to avoid revealing Earth's location. Others contend that humanity has already inadvertently exposed itself for decades through television broadcasts and other signals, rendering continued silence meaningless. Returning to the Fermi paradox itself, perhaps the most important aspect isn't finding the single correct answer, but the reflection this question provokes. It compels us to examine the path of human civilization's development, to reconsider technology's role in sustaining civilization, and to contemplate our responsibilities within the cosmos. When we gaze at the night sky late at night, pondering these grand questions, we may feel a hint of unease. Yet we might also find a peculiar sense of calm, realizing that regardless of the answer, the very fact we can pose this question is itself a remarkable achievement. The Fermi paradox and the dark forest hypothesis ultimately point in the same direction. Humanity must mature, whether confronting challenges on Earth or the possibility of extraterrestrial civilizations. We need wisdom, we need caution, and we must maintain curiosity and openness toward the unknown. In this boundless universe, we may forever be alone, or we may be watched by countless eyes, but regardless, life's pursuit of meaning, the thirst for knowledge, the yearning for connection, these alone hold value beyond the stars. Now, as you prepare to sleep, perhaps you can set aside these questions for a moment. Simply feel the miracle of existing as a being capable of contemplating the cosmos. In this moment, on this small planet, we are both stealthy travelers in the dark forest, and talkkeepers seeking companions. Whatever the truth may be, the journey of exploration itself deserves respect. Like stars in the night sky, though separated by vast distances, their light still meets in the darkness, guiding our path forward. Let us carry this contemplation into peaceful dreams, where we continue our endless cosmic exploration. When we gaze at the stars and contemplate the vastness of the cosmos, a fundamental question naturally arises. What is humanity's place in this boundless universe? The answer to this question is constantly reshaped with every new discovery. Over millennia, humanity's understanding of its cosmic position has undergone profound transformations, from the geocentric to the heliosthetic model, from the Milky Way to the observable universe. Each leap in knowledge has made us aware of our own insignificance, yet also marvel at the precious wisdom that allows us to comprehend this insignificance. That famous pale blue dot photograph perfectly captures our predicament. Viewed from 6 billion kilometers away, Earth appears as a mere 0.1 to minus pixel speck of light, floating against a vast, dark backdrop. All civilizations, all history, all love and hatred have unfolded upon this cosmic speck of dust. This realization is both humbling and exhilarating. Humbling because we recognize Earth as but a grain of sand in the cosmos. Exhilarating because we realize that life on this grain of sand can comprehend the mysteries of the universe, trace back 13.8 billion years of cosmic history, and detect galaxies billions of light-minus years away. Yet this unique position brings special responsibility. As the only known intelligent civilization in the known universe, or at least the only one currently confirmed, we bear an inescapable responsibility for the continuity of life on Earth. This fragile blue planet is the only home we know. Protecting it is not only for ourselves, but also for this precious spark of wisdom in the cosmos. From a broader perspective, humanity may be undergoing a critical transition, from a species shaped by natural selection to a civilization capable of actively shaping its own future. This shift presents both opportunities and immense risks. Nuclear weapons, climate change, biotechnology, artificial intelligence, all may become trials on our path forward. Contemplating these issues on a cosmic scale helps us transcend short-sighted disputes and recognize that humanity is fundamentally a community with a shared future. Differences in nations, races, and cultures seem so insignificant against the backdrop of the vast universe. We must learn to confront challenges as a unified whole. The arrival of interstellar visitors further underscores this interdependence. When UMUA and Boris of comets traversed our solar system, they belong to no single nation. Their discovery and study resulted from global scientific collaboration. This transnational scientific cooperation may well serve as a template for humanity's future. Our responsibility extends to how we treat potential extraterrestrial life, whether microbes within our solar system or future intelligent civilizations we may discover. All demand we approach them with caution, respect, and wisdom. The dark forest hypothesis cautions us to be vigilant, but it must not extinguish our courage to explore. As sentient beings in the cosmos, we bear a unique mission to comprehend the universe and preserve its knowledge. Should human civilization one day perish, the knowledge and achievements we've accumulated would vanish with it. This would be an immense loss to the cosmos, for as far as we know, we are one of the ways the universe understands itself. This realization bestows upon us the responsibility to preserve and disseminate knowledge, from placing monuments on the moon to sending probes into interstellar space carrying human messages. These actions serve not only to communicate with other civilizations, but also to leave evidence of humanity's existence in the river of time. Every person living today is participating in writing the story. Our choices will determine the course of human civilization, whether it drifts toward fragmentation and myopia, or uniting to confront shared challenges. This choice concerns not only our future, but the very survival of this precious flame of consciousness in the cosmos. As we gaze at the night sky late into the night, let us imagine the possibilities of the future. Perhaps one day humanity will become an interstellar species, sowing the seeds of life across other worlds. Perhaps we will encounter other intelligent beings, opening a new chapter in cosmic civilization exchange. Perhaps we will unlock the ultimate mysteries of the universe, understanding the essence of space minus time and existence. Wherever the future may lead, every action we take today lays the foundation for that future, protecting Earth's ecosystems, fostering peaceful human cooperation, advancing the healthy development of science and technology, nurturing the spirit of exploration in the next generation. These seemingly ordinary acts are, in fact, contributing to the continuity of human civilization. On this tranquil night, let us remember, though we are insignificant in the cosmos, our choices, our actions, our love and wisdom may carry cosmic significance. We are the eyes through which the universe perceives itself. the mind through which it contemplates its own being. Armed with this awareness and sense of responsibility, we can face life's challenges with greater serenity, for we know that every act of kindness, every pursuit of truth, every decision to protect life, adds a touch of beauty to this universe. Now close your eyes in peace. Let this cosmic contemplation flow into your dreams. In your dreams, perhaps you will see human civilization twinkling like starlight across the cosmos, small yet steadfastly shining, illuminating the path ahead, guiding us toward a brighter future. As we gaze at the twinkling stars beneath the night sky and envision humanity's grand future of cosmic exploration, a series of space missions currently in planning and development are poised to usher us into an unprecedented interstellar era. These missions will fundamentally transform our relationship with the universe. Let us approach these upcoming cosmic journeys with the utmost serenity. The first to embark will be the Mars Sample Return mission. This ambitious joint venture between NASA and the European Space Agency will accomplish this epic mission through 3 launches. The Perseverance rover has diligently worked in G0 crater to meticulously collect and seal dozens of Martian rock and soil samples. The Sample Return lander is scheduled for launch in 2028. It will achieve the first autonomous takeoff on the Martian surface. It will deliver the precious sample containers into Mars orbit. Finally, the Earth Return Orbiter will complete the relay, bringing these priceless treasures back to Earth in the early 2030 seconds. Meanwhile, China's Tianwen-3 mission is also in full swing. This mission, similarly aimed at Mars sample return, is scheduled for launch in 2028. It will mark another milestone in China's space history. If all goes well, by the early 2030 seconds, humankind will possess field samples from 2 planets for the first time. This will not only deepen our understanding of Mars' evolutionary history, but also lay the groundwork for future crewed missions to the Red Planet. Venus, our long-minus neglected sister planet, is poised to enter a new golden age of exploration. NASA's Da Vinci mission, slated for launch in 2029, will carry a rugged descent probe through Venus's thick sulfuric acid clouds to precisely measure atmospheric chemistry during descent, which may help unravel the mystery of Venus's runaway greenhouse effect and explain why a planet so similar to Earth evolved along such a different path. Accompanying Da Vinci is the Veritas mission. This orbiter will use advanced synthetic aperture radar to penetrate Venus's permanent cloud cover, mapping Venus's surface topography with unprecedented resolution. The synergistic work of these 2 missions will reveal Venus's geological history and help us understand the evolutionary patterns of terrestrial planets. Europa, this icy world of Jupiter's moons, has long been a prime target in the search for extraterrestrial life. NASA's Europa Clipper mission, scheduled for launch in 2024, will carry 9 the -art scientific instruments, to perform over 40 close flybys of Europa, using radar to probe the subsurface ocean and mass spectrometers to analyze water vapor plumes from icy cracks. We may soon discover whether this underground ocean harbors conditions suitable for life. Even more anticipated is the Dragonfly mission. This innovative rotorcraft will launch in 2027. To tighten Saturn's moon rich in organic molecules, Dragonfly will conduct multiple landing flights at various Titan locations to study the planet's chemical composition and habitability. Titan's dense atmosphere and low gravity make rotorcraft flight an ideal exploration method. This will mark humanity's first aircraft exploration of a deep space object. Looking further ahead, interstellar probe missions are in the conceptual design phase. This ambitious plan aims to fly beyond the heliosphere into true interstellar space. If approved, it would launch in the 2030 seconds, using Jupiter's gravitational slingshot effect to accelerate to an astonishing 15 to 20 kilometers per second. In less than 50 years, it could reach a point 375 astronomical units from the Sun. This distance far exceeds the journey undertaken by Voyager 1. Exploration missions targeting interstellar visitors are also under active consideration. The Comet Interceptor project being studied by the European Space Agency is designed to rapidly alter its trajectory for rendezvous and investigation upon the discovery of the next interstellar object. This ingenious design positions the probe at a Lagrange point within the Earth-Sun system, like a patient hunter awaiting the right prey. Upon detecting a suitable interstellar visitor, it can immediately set off for interception. China's space exploration also demonstrates remarkable ambition. The planned Zhenghe interstellar probe aims to conduct in-depth exploration of the asteroid belt and Jupiter system. Named after the great Ming Dynasty navigator, this mission symbolizes the Chinese nation's eternal pursuit of the unknown. Scheduled for launch around 2030, it will not only visit main-belt asteroids, but may also fly past Jupiter's Trojan asteroids. Japan maintains its lead in asteroid sample return. The Hayabusa 3 mission is currently in planning. This time it will attempt sample collection from a carbonaceous asteroid. These asteroids preserve the solar system's most primordial chemical composition, potentially holding key clues to the origins of life. Planned for launch in the late 2020 seconds, return to Earth in the 2030 seconds. Private space companies are also emerging in deep space exploration. SpaceX's planned Red Dragon mission aims to validate unmanned Mars landings, paving the way for future crewed Mars missions, while Blue Origin's Blue Moon lander focuses on establishing sustainable lunar bases as staging posts for deep space exploration. In observational technology, a new generation of ground-based and space telescopes is poised for deployment. The Verisi Rubin Observatory's Legacy Survey for Time will conduct repeated observations of the entire visible sky over a decade, anticipated to discover dozens of new interstellar visitors, greatly expanding our opportunities to study these cosmic wanderers. Successors to the James Webb Space Telescope are also in planning stages, such as the Large Ultraviolet Optical Infrared Survey Telescope, which will possess a field of view 100 times larger than Hubble, enabling direct imaging of the exoplanetary atmospheres to search for potential signs of life. In propulsion technology, multiple breakthrough studies are underway. Solar sail technology has been validated in orbit. The Light Sail 2 mission successfully demonstrated the ability to use solar pressure for orbital augmentation. Future interstellar missions may employ more advanced solar sails, combined with ground-launched laser propulsion, to achieve unprecedented flight speeds. Nuclear thermal propulsion technology is regaining attention. NASA's Draco project is developing a new generation of nuclear propulsion systems. This technology could reduce travel time to Mars to under 100 days, creating better conditions for crewed Mars missions. Electric sails represent another intriguing concept. By emitting positively charged filaments that interact with protons in the solar wind to generate sustained thrust. Though minimal, this thrust can persist for years, making it ideal for long distance interstellar voyages. Cutting-edge breakthroughs also include third-generation gravitational wave detectors like the Einstein telescope, capable of detecting fainter ripples in space-time. Perhaps one day they will reveal the superluminum communication methods used by extraterrestrial civilizations. These upcoming missions and technological advancements are not merely about answering scientific questions. They represent humanity's resolute strides toward the cosmos. Every launch, every new discovery, expands the boundaries of our understanding and reshapes our place within the universe. As we lie in bed and imagine these probes navigating the cosmos, we feel a wondrous connection. They are extensions of human consciousness, carrying our curiosity and dreams toward distant realms we cannot yet reach ourselves. Every data point gathered from these missions will enrich our understanding of the cosmos. Perhaps in the not to distant future, data transmitted by a probe will fundamentally alter our perception of life's place in the universe. Now close your eyes. Let these impending cosmic journeys lull you to sleep. In your dreams, you may board these advanced probes, traverse the asteroid belt, soar through Jupiter's clouds, and explore mysterious worlds we've only begun to understand. At the dawn of this interstellar age, everyone can participate in this grand adventure through imagination, previewing the universe's mysteries and tranquil dreams. As we envision the bright future of interstellar exploration, we must remain acutely aware of the formidable obstacles ahead. These technological challenges test not only our engineering prowess, but also represent the ultimate trial of human ingenuity. The foremost challenge in deep-space exploration lies in propulsion systems. Conventional chemical propulsion has approached theoretical limits. Its specific impulse falls short of interstellar travel requirements, though nuclear thermal propulsion offers higher efficiency. Reactor miniaturization and safety remain intractable issues. More advanced fusion propulsion remains experimental, with a long journey ahead before practical application. Power systems present another critical challenge. Beyond Jupiter's orbit in deep space, solar panel efficiency plummets dramatically. Relying on nuclear power sources becomes imperative. However, existing radiospire thermoelectric generators offer limited power and are prohibitively expensive. Developing safer, more efficient nuclear battery systems has become an urgent requirement for deep-space missions. Communication delays increase significantly with distance. Mars-Earth communication delays can reach 20 minutes. In the outer solar system, delays extend 2 hours or even days. This renders real-time control of probes impossible. Probes must possess high autonomy, capable of independently handling various unexpected situations. Radiation protection poses a severe challenge for crewed missions. Without the protective shield of Earth's magnetic field, astronauts face intense cosmic radiation exposure. Long-term exposure may increase cancer risks and impair central nervous system function. No perfect radiation protection solution currently exists. Heavy shielding layers increase launch weight, while magnetic deflection technology remains conceptual. While discussing technical challenges, we must also consider deeper ethical questions. Planetary protection principles require us to avoid contaminating other celestial bodies. This safeguards potential life forms while preserving their scientific integrity. However, as exploration activities intensify, striking a balance between discovery and preservation demands careful deliberation. The possibility of extraterrestrial life introduces ethical dimensions to our exploration. If microbial life is discovered, do we have the right to alter its environment? If intelligent life is encountered, how should contact protocols be established? These questions require global collaboration. Resource utilization also sparks new ethical reflections. Asteroid mining could yield immense economic benefits, but should private companies be permitted to claim extraterrestrial resources? How can we ensure equitable access to space resources and prevent new forms of space colonialism? These demands necessitate corresponding international regulations. Gene-editing technology in long-duration space missions may be used to enhance astronauts' physical capabilities. Yet is such modification ethical? Can genetically altered humans still be considered purely human? Discussions on these issues must precede technological advancements. Artificial intelligence plays an increasingly vital role in deep space exploration. However, fully autonomous AI systems operating independently on extraterrestrial planets could generate unforeseeable consequences. We must establish ethical guidelines for AI systems to ensure their actions align with human values. The space debris problem is escalating. Near-Earth orbit is already saturated with various fragments that threaten normal space activities. How to clean up this debris? How to regulate future space activities? Avoiding the creation of new debris. These are all urgent issues requiring resolution. Plans to establish permanent bases on the Moon and Mars have sparked discussions about extraterrestrial territorial sovereignty. The 1967 Outer Space Treaty prohibits nations from claiming extraterrestrial territories, but the legal status of private enterprises remains ambiguous. The international community must urgently refine relevant regulations. The enormous costs of deep-space exploration have also sparked societal debate. Some argue these funds should be directed towards solving Earth's problems. Supporters, however, contend that technological advancements from space exploration will ultimately benefit all humanity. Both perspectives warrant serious consideration. The dissemination of information from interstellar probes also raises ethical questions. When signs of potential life are detected, should the discovery be immediately disclosed or first verified? How can unnecessary panic be avoided? Establishing clear guidelines for information release is essential. With private enterprises entering space exploration, conflicts may arise between commercial confidentiality and scientific sharing. How to ensure vital scientific discoveries benefit all humanity while protecting legitimate corporate interests requires finding a balance. In the search for extraterrestrial life, we must also consider the risk of reverse contamination. Samples brought back from other planets may contain unknown microorganisms. How to safely study these samples, preventing impacts on Earth's ecosystems. Strict safety protocols must be established. The psychological impact of long-duration spaceflight on astronauts is another critical ethical concern. During prolonged solitary missions, how can we safeguard astronauts' mental health? Should psychiatric medications be permitted? These matters require oversight by medical ethics committees. The rise of spacetourism presents new challenges. While affluent individuals can experience spaceflight, it remains inaccessible to the general public. Will this exacerbate social inequality, or will it, like other historical technologies, eventually become accessible to all? When developing extraterrestrial resources, we must consider impacts on the original environment, even if devoid of life. These unique geological environments hold scientific value. We should preserve certain areas as cosmic heritage for future researchers. As human activities expand into space, we must redefine cultural identity. For humans born and raised in space, how will their cultural affiliations evolve? How should we document and safeguard these emerging cultural forms? As we conclude these reflections, we must recognize that technological advancement and ethical consideration must advance hand in hand. Every technological breakthrough should be accompanied by corresponding ethical discourse. Only then can we ensure space exploration truly benefits all humanity, rather than creating new problems and conflicts. These challenges may seem daunting, but humanity grows precisely through overcoming difficulties. Through international cooperation and thorough discussion, we will surely find the optimal solution balancing all interests. Now, as night deepens, let us temporarily set aside these complex thoughts. Trust that human wisdom and goodwill are sufficient to meet the challenges ahead. In your dreams, perhaps you will glimpse a beautiful future where humanity coexists harmoniously with the cosmos, a future holding both boundless treasures of knowledge and profound reverence for life. With such anticipation, let us drift into peaceful slumber under the watchful gaze of the stars, continuing our shared cosmic dream. In the vast journey of cosmic exploration, professional scientists undoubtedly play a pivotal role. Yet every ordinary person who holds curiosity for the starry sky can equally become a participant in this grand endeavor. Astronomy may be the most democratic of all sciences. Its laboratories stand open to all, requiring only a heart's yearning to explore. Citizen science projects offer the most direct pathway for public participation. These meticulously designed online platforms present authentic scientific data to everyone. The Galaxy Zoo project exemplifies this perfectly. When researchers faced millions of galaxy images needing classification, they chose to seek help from the public. Surprisingly, participants exceeded expectations. Not only did they complete the massive data classification task, but they also discovered unique celestial objects that professional astronomers had overlooked. For instance, the rare Hanon galaxy type was identified by a Dutch teacher participating in the project. In the field of planet hunting, NASA's Exoplanet Hunter project enables ordinary people to analyze light curves from the TSS Space Telescope. By identifying periodic dips in stellar brightness, participants help pinpoint potential exoplanets. Dozens of amateur astronomers have become co-authors on scientific papers due to their discoveries. This recognition belongs not only to them individually, but also showcases the power of collective intelligence. in the search for interstellar visitors. The public similarly plays a vital role. Every night, amateur astronomers worldwide scan the skies with their telescopes. Some build professional -grade observatories in their backyards, others form observation networks to share data. The discoverer of Comet Borisov in 2019 was an amateur astronomer from Crimea using a homemade telescope. He found humanity's second interstellar visitor. The proliferation of smartphones has opened new avenues for public participation. Numerous astronomy observation apps can transform your phone into a scientific recording tool by measuring stellar brightness, logging meteor appearances, or even monitoring the darkness of the night sky. These seemingly simple observations collectively form valuable scientific data. Public involvement is particularly crucial in light pollution monitoring. The Global Dark Sky Project invites people worldwide to observe designated constellations on specific nights and record the faintest visible star magnitude. This data helps scientists create global light pollution maps, providing crucial evidence for dark sky preservation. Public involvement in data analysis is also growing. Some enthusiasts specialize in studying publicly available astronomical data using open-source software for deep mining. Some search for anomalous orbits in asteroid data. Others seek unusual signals and radio data. These independent verifications and discoveries offer valuable supplements to professional research. For hands-on enthusiasts, building their own radio telescopes has become a reality. Open-source projects provide detailed blueprints using readily available components to construct small radio telescopes capable of receiving cosmic signals. Though performance falls short of professional equipment, the experience of personally receiving signals from space is unparalleled. In education, teachers and students engage directly in astronomical research through numerous initiatives. NASA's Lunar Observation Program enables schools to borrow small telescopes for lunar observation. The European Space Agency's TRAIN program allows students to operate professional telescopes for observations. These experiences often plant the seeds of scientific curiosity in young minds. In software development, programming enthusiasts can contribute code to astronomical projects, from data processing algorithms to visualization tools. From observation planning software to simulation programs, the open-source astronomical software ecosystem welcomes every capable individual to participate in its refinement. Social media has also become a vital platform for public engagement. Astronomy enthusiasts on Twitter, Weibo, and other platforms share observational results and discuss the latest discoveries, forming vibrant online communities. When special celestial events occur, these communities often gather global observation reports in real time. For artists, astronomical discoveries provide an endless wellspring of inspiration. Through painting, photography, music, literature, and other forms, artists help disseminate scientific knowledge, bringing the beauty of astronomy to a wider audience. This fusion of science and art enriches humanity's cultural treasury. Another vital form of public engagement is supporting science outreach by watching educational videos, attending astronomy lectures, visiting planetariums and science museums. The public not only gains knowledge, but also fuels the sustained growth of science communication. Every individual captivated by the night sky infuses vitality into the entire astronomy community. In the era of telescope sharing, remote observatories enable more people to conduct professional -level observations, even from cities with severe light pollution. Connecting to remote telescopes at premium sites like Chile or Hawaii provides access to high-quality observational data. The widespread availability of such services significantly lowers the barrier to conducting serious astronomical research. For observers who enjoy challenges, searching for supernova offers an exciting avenue. Some amateur astronomers have discovered dozens of supernovae by systematically comparing galaxy images. These discoveries provide invaluable data for studying stellar evolution. Public participation is particularly crucial in protecting the night sky. Joining organizations like the International Dark Sky Association and participating in dark sky preservation activities helps reduce light pollution ensuring future generations can also enjoy the brilliant night sky. This is a profoundly meaningful endeavor. Regarding funding support, crowdfunding platforms offer new avenues for innovative astronomy projects. From small satellites to observational equipment, from data processing software to public outreach activities, the public expresses support for specific research directions through direct funding. This model brings scientific research closer to the people. For theoretical researchers, even without a professional background, one can engage with academic papers, participate in online discussions, and propose novel ideas. Many groundbreaking insights in scientific history originated from thinkers outside traditional academic circles. In the upcoming era of the Vera Rubin Observatory, it is projected to generate 20 TB of observational data nightly, offering unprecedented opportunities for public participation. By assisting in classifying this vast data, ordinary individuals may discover the next MUA, or some previously unseen astronomical phenomenon. Every individual contributing to astronomical discoveries, regardless of the scale of their contribution, is adding a brick to humanity's quest to understand the cosmos. This endeavor belongs to no single nation or institution, but to all of humankind, to every soul who gazes at the night sky and is captivated by its wonder. As you prepare for sleep tonight, consider this thought. Perhaps just tonight, some ordinary person in their backyard or through a computer screen is making a new contribution to astronomy. This sense of connection, this shared joy of exploration, is one of the most beautiful gifts the universe bestows upon us. Under the witness of the stars, everyone can become an explorer and write their own line in the grand story of the cosmos. Let us embrace this belief as we drift into peaceful dreams and continue our endless cosmic exploration in our sleep. When we gaze at the stars again tomorrow night, it may be your moment to uncover a new cosmic mystery. As interstellar visitors, MUA and Comet Borisov quietly depart, they leave behind not only unsolved mysteries, but a profound and enduring series of scientific revelations. These insights, like gifts bestowed by the cosmos, are reshaping our understanding of ourselves and the universe. Interstellar visitors first reveal to us that the cosmos is a space teeming with dynamic exchange. Star systems are not isolated islands, but interconnected through countless interstellar materials that traverse between them. This realization fundamentally transforms our understanding of the solar system. We are no longer a closed island in the universe, but an active participant in the vast ecosystem of the Milky Way. Each arrival of an interstellar visitor serves as clear evidence of the grand cosmic cycle of matter. The diversity of these visitors is equally thought-provoking. MUA's peculiar shape and behavior, alongside Borisov's classic cometary features, reveal that the forms and properties of interstellar objects may be far richer than we imagined. Like to travelers from different worlds, bearing unique imprints of their homelands, they remind us that the universe's creativity is boundless. In terms of observational technology, the arrival of interstellar visitors has exposed the limitations of existing sky-survey systems. Yet it also points the way forward. We need more sensitive telescopes, faster response mechanisms, smarter data processing algorithms. These challenges are driving technological innovation across the entire field of astronomy. Every technological breakthrough will enable us to better listen to the subtle whispers of the cosmos. The study of interstellar visitors also demonstrates the essence of the scientific method. When to emulate Scientists did not dismiss observational data, but chose to expand and refine theories. This openness to the unknown is precisely what enables science to advance. Every anomalous phenomenon heralds a scientific breakthrough. These cosmic visitors also prompt us to reconsider life's distribution across the cosmos. If interstellar objects are so common, then the organic molecules forming the basis of life may be widely disseminated throughout the universe. The seeds of life may well be carried aboard these interstellar travelers, scattering them across different star systems. This vision is exhilarating and makes the cosmos seem more vibrant with life. From an engineering perspective, studying the motion patterns of these interstellar visitors could offer insights for future interstellar voyages. How do they adjust their orbits without consuming propellant? How do they maintain structural integrity during their long journeys? The answers to these questions may lie hidden within the data we've already collected, awaiting discovery by those with the will to seek them. The arrival of interstellar visitors also underscores the importance of international collaboration. When these moving celestial bodies appear, no single nation can complete all observations alone. Close cooperation among the global astronomical community enables us to gather as much scientific data as possible within a limited time frame. This collaborative model provides a blueprint for humanity to address other global challenges. On a philosophical level, interstellar visitors make us realize the universe is both familiar and alien. The similarities between Comet Borisov and Solar System comets reveal the existence of unified physical laws across the cosmos, while MUA's unique properties remind us that each star system possesses its own distinct characteristics. This coexistence of unity and diversity is one of the most captivating traits of the universe for astronomy education. The stories of interstellar visitors ignite the imagination of countless people. Their mystique, the scientific debates they spark, their unsolved enigmas, all serve as excellent vehicles for communicating scientific knowledge to the public. In this process, we not only impart knowledge, but also cultivate critical thinking and an exploratory spirit. From a longer term perspective, studying interstellar visitors may help us answer the age-old question: are we alone in the cosmos? If interstellar objects are so common throughout the universe, then the emergence of life may not be rare either. While this inference requires further evidence, it has already injected new momentum into the search for extraterrestrial life. Interstellar visitors also teach us humility. Before MUA, we weren't even certain interstellar objects existed. After MUA, we realized how much of the universe remains unexplored. This shift in perception reminds us to maintain an open mindset and prepare for the next unexpected discovery. In studying these cosmic visitors, we have also developed new observational and analytical methods that are not only applicable to interstellar objects, but are also being applied to other celestial bodies within our solar system. Scientific progress often unfolds this way. Tools created to solve one problem become keys to unlocking others. Now, as we look back on this journey of exploration, we see that interstellar visitors have brought us far more than just scientific data. They have transformed how we perceive the universe, enriched our research methodologies, and expanded the boundaries of our imagination. These gains will profoundly influence the future of astronomy, guiding the direction of future exploration. In this quiet moment, as we gaze upon the starry sky, imagining those interstellar travelers still journeying through the cosmos, perhaps we can sense a special connection between us and them. Though our encounters were fleeting, we share in the grand narrative of the universe. This story continues, its next chapter awaiting us to write. Let us carry these revelations with curiosity for the unknown as we continue our journey of cosmic exploration. Every step may bring new discoveries. Every discovery may reshape our understanding. This is the most captivating aspect of science and the most beautiful blossoming of human intellect. Now, please close your eyes. Let these cosmic revelations accompany you to sleep. In your dreams, perhaps you will meet the next interstellar visitor. Journey with it across the Milky Way. Explore the cosmic mysteries we have yet to uncover. In this endless voyage of discovery, everyone is a participant. Every dream is a new beginning. When you lie in bed after a busy day, the stars outside your window may seem distant and quiet. But remember, this stillness is not emptiness. It is a universe brimming with infinite possibilities awaiting our exploration. Everyone can be a participant in this great quest. Imagine this: when you capture a shooting star streaking across the night sky with a mobile app, you're contributing invaluable data to scientific research. When you identify constellations with your child, you're passing on humanity's millennia-old spirit of inquiry. these seemingly small actions are actually vital pieces in the puzzle of cosmic exploration. We live in an extraordinary era where technological advances allow ordinary people to reach for the stars. A small telescope lets you see Jupiter's stripes. A simple camera can capture the intricate details of the lunar surface. Scenes once reserved for astronomers alone are now landscapes accessible to everyone. Curiosity requires no grand justification. Simply spend a few minutes on a clear night, gazing up at the stars, and feel that connection to the vast cosmos. This experience helps us transcend daily worries and view life through a broader perspective. The most wondrous aspect of scientific exploration is its perpetual capacity for surprise, just as the appearance of Oumuamua was utterly unexpected. The next major discovery may well stem from your or my participation, perhaps through analyzing publicly available astronomical data or by documenting an unusual observation. Each of us could become the next discoverer. In this process, we explore not only the external cosmos, but also our own inner selves. Every gaze upon the starry sky sparks contemplation about life's meaning. This dual exploration of inner and outer worlds enriches and deepens our lives. Don't be daunted by the grandeur of questions. It is precisely these eternal questions that propel humanity forward. We may never know all the answers, but the pursuit itself holds profound value. Like stars in the night sky, though distant and unreachable, their light continues to guide us. Modern technology offers unprecedented opportunities for participation. You can join online science projects to help astronomers analyze data. You can use telescope-sharing services to observe distant galaxies. You can even form your own observation group to explore the cosmos with like-minded people. Remember, science is not the privilege of a few, but a shared endeavor for all humanity. As you read these words, countless ordinary people worldwide are contributing to scientific exploration. Their backgrounds vary, their ages differ, yet they all share the same curiosity about the universe. To our younger friends, you live in a wonderful era, with unprecedented learning resources and opportunities to participate. Hold on to your curiosity, ask questions boldly, and seek answers persistently. The mysteries of the universe await you to uncover. To those busy navigating life's demands, you may feel no time to gaze at the stars, but exploration can be simple. It could be listening to a science podcast during your commute, or watching a documentary during your downtime. These small moments add poetry to our lives. We encourage you to cultivate your own exploration habits. It could be learning about a star each night with a sky map app, setting aside half an hour weekly for stargazing, or joining a monthly online science lecture. These habits will open a window to the cosmos. Along your journey of discovery, you'll meet like-minded companions. Astronomy boasts a warm global community where people delight in sharing knowledge, helping one another, and growing together. Joining such a community will make your exploration journey richer and more vibrant. Don't be afraid to ask questions. Every astronomer was once a beginner full of questions. Every great discovery began with a simple question. Your questions might spark important insights. Your curiosity might bring fresh perspectives. We also encourage you to share the joy of discovery with others. When you teach a child to recognize the Big Dipper, when you explain the phases of the moon to a friend, you are not only spreading knowledge, but igniting more curiosity. This passing of the torch is one of humanity's most beautiful traditions. In this age of information overload, we need to cultivate independent thinking even more. Learn to discern scientific truth from falsehood. Maintain critical thinking. Avoid blindly following authority, and don't take rumors at face value. Cultivating this scientific spirit is more vital than any specific knowledge. When you feel lost or confused, look up at the starry sky. Those lights traveling tens of thousands. Whisper of the universe's eternal vastness. Our troubles seem so insignificant on a cosmic scale, yet this smallness is not discouraging. It is liberating. The journey of exploring the cosmos is fundamentally a spiritual practice. It teaches us humility. Because we are so insignificant in the universe, it also teaches us courage, because we dare to explore such vast unknowns. This unity of opposites is the most moving aspect of the human spirit. Know as you prepare to drift off to sleep, carry with you this conviction: tomorrow marks the beginning of new explorations. Each dawn brings fresh possibilities. Each night conceals fresh mysteries. The universe's story continues to unfold, and you are both its reader and its chronicler. Let us meet again on the next clear night, gazing together at the starry sky, continuing this endless quest under the witness of the stars. We shall create the dialogue between humanity and the cosmos. This dialogue stretches from ancient times into the future. You and I are indispensable notes within it. Good night, dear explorer. May starlight illuminate your dreams. May curiosity accompany your tomorrow. In this infinitely vast cosmos, our exploration never ceases. Our hope forever shines. When you gaze upon the stars, those lights traveling millions of years, gently soothe the anxieties of the day. The scale of the cosmos makes us realize how insignificant our troubles truly are, and we who contemplate the stars are truly precious. Every gaze upward at the night sky is a conversation with the infinite. Planets orbit along fixed paths. Galaxies follow established laws. This cosmic order brings profound peace to the soul. Astronomy tells us we are all stardust, sharing the deepest kinship with the cosmos. This realization brings warmth. No longer alone. Let the universe's tranquility flow into your heart, carrying this eternal peace. Sleep soundly. In your dreams, you may traverse nebulae, stroll through the Milky Way, dance with the stars. Good night. May the universe's serenity dwell within you.